っていうのをフラムで分析した上でシミュレーションするという大変面白い、ご発表をされます。So, David, please start.
Thank you. Ohayou gozaimasu. Thank you for inviting me. Just before I start, could I mention, could I compliment the last speaker? That was a very, very interesting talk. Very, very interesting. It reminds me of the work we did on the brain with the FRAM, because it fits into the way the brain works. You know, if you're playing the piano, for example, the learner, he has to concentrate on the keyboard and he has to concentrate on reading the music, whereas the expert musician, he can think about the beauty of the music, etc. So it all fits very, very well into a picture of how we process information. So anyway, thank you for inviting me. I'd like to talk a little bit about something we've been doing with the FRAM modeling, and in fact, something Reese Hill, who is developing a software for the FRAM model visualizer. And we've applied this as a test case. So I'd like to talk about FRAM as a whole systems approach and use the Formula One pit stop as a test case. So the background to this is somewhat interesting. In Cardiff, we have a group which consists of clinicians, doctors, business study people, and also engineering people. And we're trying to help the hospitals to reduce the inadvertent infection with COVID-19. And what we're trying to do is improve the way in which emergency departments operate and handle patients. So this is a very, very relevant application of FRAM, but one which has a lot of challenges. We've already used FRAM to identify some improvements which have debottlenecked the process. And for example, in improving the triage process and improving the way in which patients are referred and information is handled, all of this has speeded up the process and helped us identify where the problems arise. But we want to take this a little bit further, because in the NHS, in the National Health Service in the UK, the time taken to handle a patient is a critical metric. They're still on the old targets and the old way of handling industrial processes, and they have these metrics. So we have access to the throughput data, the average time, the sort of statistical process control data for patient flows through hospitals. So we have a lot of this data, very detailed data, which goes back 2 or 3 years. And we want to really use this data in helping us further improving the FRAM adaptability. But to date, in fact, we haven't been able to use it because the time taken, which is what these times are, is somewhat difficult to do with FRAM at the moment. And there's a lot of confusion in the way in which we use FRAM at the moment to complement or implement the time data. But before I go on to it, I'd just like to acknowledge that the key work on the software was done by Reese Hill, and he's constantly improving the FMV. Professor Manish Kumar, who is from the business school, who has the expertise in the operational research, the lean tools, etc., which we're using. And Professor Ben Ala from the Netherlands, who is a risk analyst expert. So together we worked on providing this additional, I think, dimension, we hope, to FRAM. So if you're using data, time data, you have to have some model of the system. And to date, most models of the systems that have been used for these lean processes have been these kind of business process modeling diagrams, which give you sort of one node at a time, linear progress. And even if you have multiple swim lanes in the BPM, you still have this sequential, ordered, predetermined map of what the process is doing. Even the later safety studies that have been used, things like Swiss cheese, bow ties, and barriers, have really looked at the system as a kind of a black box, as a fixed, unchanging entity. And what you're looking to do then is to provide the barriers and the reassurances that the system will not fail by putting in things to support this choreographed model, this predetermined black box model of what the system does. But that's in a way a little bit losing the details of what's happening. And even if you use things like AxioMap and STAMP, these are still static system pictures. And in the case of STAMP, these are control circuits of a circuit diagram, which is fixed. And all you're doing really is mapping what happens on this single picture. So what we'd like to do then is look at the system, which is not a circuit diagram, but a socio-technical complex system, something like healthcare, which needs a lot more, if you like, understanding of what's actually happening in the detail. And what we're using is FRAM, which, as you've seen before in the previous presentations, allows you to look at the whole system and how all these functions are interacting. It's a visualization which gives you this opportunity to look at the feedbacks, the things that you wouldn't pick up from simplistic circuit diagrams. So we can look at things like what if. What are the outcomes? How does this function progress? What is the effect of the output of this function on other functions, etc. And this then can give you the as we saw in the last picture, last presentation, how different outputs come back and have inputs or have effects which are unexpected in some cases. But again, to date, mainly we've been using one single FRAM and look at the effects, for example, resonance of one function affecting another function downstream. So and again, even things like Doug Smith in Canada has been using FRAM to try and track icebreakers through ice fields. But again, this is essentially one FRAM picture, and you're tracking single functions through that field. And again, as we saw in the last presentation, the very nice work of Hirose doing the fuzzy FRAM, it's taking a single FRAM instantiation and tracking the way in which the fuzziness, the probability of failure of the different functions progresses through that system. But what we're looking at in most cases and in most analyses, as you see them, is what we call a FRAM instantiation, which is in effect a time slice. And at every point in the process, you have a different time slice. So a process is a complex system. A process in a complex system is then a sequence of these FRAM instantiations. They're not necessarily rigorous in time, but they are slices of what's happening in the whole system at that particular point in time. And the development of the next instantiation then depends solely on what the functions are doing in that particular instantiation. And this, as we saw, is a very nice way way of following processes in the Markovian constraint, which is that behaviors in the next instantiation can unexpectedly emerge from an unusual combination of functional properties in the current time slice. And they also can be affected by the emerging states of other functions in the system. So this is quite a complex process to handle in terms of how does time affect a process. It's not a linear operational research type of application. We have to have much more sophisticated analysis of what time is doing. And the reason for that is that time is an enigma, because in most systems, these functions are not necessarily coordinated. They're mostly out of sync. They don't vary together. There's no regimented or preset way in which these functions are going to work. So they are essentially asynchronous, which means basically that they do interact, but they don't occur at predetermined intervals and do not necessarily rely on each other's existence to function. So these things are happening, they're doing their own thing, they have their own agendas. And this is quite difficult then to model in terms of preset algorithms. And this actually does reflect reality. In a real life system, there's a whole lot of things going on, a whole lot of independent effects, a whole lot of background effects. The CPCs in the last presentation, these all affect these functions. They all affect what's happening. So essentially, functions are unpredictable, as we've seen, but they operate in an unpredictable soup of functions, all in various states of suitability, availability for interacting. And this is very difficult for a process flow, for a conventional process flow, a stamp or an aximap diagram to kind of represent. Okay, we've got a picture of what the system structure looks like, but do we have a way of then following that development of the emerging processes as they pan out? So for FRAM then, which is still very useful, we can define an instantaneous state for every function that is active. But how do we put these together into an overall property of that instantiation, which is perhaps a behavior which is specific to that point in time? So we need to address two things then. How these functions, the state of these functions is affected by its own properties. It's endogenous. How does it behave autonomously? How does it behave in isolation? And the second thing which FRAM normally does is, how is a FRAM function affected by its interaction with other functions? This is the normal and very useful way that FRAM is operated. But now what Reese has given us with the FRAM model visualizer is an aspect which or an additional facility, which is metadata. And the metadata takes the FRAM approach and then additionally allows us to specify what the state of a function is and define this with a set of metadata values. So how effective is that function? How available is it? How long is it taken to execute? How vulnerable is it to other aspects, etc.? All these things we can now put in as metadata into a function. And again, how is it affected by the states of the other functions, which are also modulating as the instantiations develop. So all of this is very interesting extra data now, which we can put into a FRAM function. And Reese has now provided us a facility to allow us to do that. And this facility comes up on the normal FNV, which allows you to specify for a specific function, when you click on the function, a key, which is defining a property of that function that you want to specify. And then you can assign a value to it, or you can in fact calculate it from what all the other functions in the instantiation are doing, or maybe what its own properties have been in the previous instantiation. So you have a way of specifying different states. You have a way of identifying how those states behave, how that states will behave given what everything else in the system is doing, and then being able to assign a value to it. And this is very interesting to us because obviously then time is one of the things that we can assign to that function, how long it takes to perform a task in a process. What are the control constraints? What are the arrival rate of the inputs, the process rates of the outputs, its interaction with other processes, its expected waiting time before it can actually operate. And these come in from much broader aspects from other functions, background functions, foreground functions. The total time taken for the system so far, if you like, is a thing that we can now accumulate. The rate of delivery of input depends on the rate of production from other functions. The inventory constraints, for example, time taken for resources and conditions to be met. We can now put in the depletion of resources. We can now put in maybe vulnerability of resources, time for preconditions to be met. How effective is the control system in terms of timing? Have we got control systems there in time? So we have a whole new set of values that we can assign to this particular functions. And the reason we're doing this is that we are operating in a very complex system. In ICU in a hospital, it's a very high stress, very dynamic, time critical operation. You have teams working in very close cooperation, and they operate with, again, very, very well worked out protocols. For example, in ICU trauma, they got A, B, C, D. A, check the airway, B, the breathing, C, cardiac, etc. All these things are routine, but every patient is different, and every response to a particular set of symptoms is different. So although you got a preset program, a preset business process model, actually, when you get right down to it in a theater situation, then it has to adapt to what it sees there. And what we're looking for then is a test case which approximates to this high stress, high speed system. So we need to select it, and we need to be able to populate with enough information to build the FRAM. And what we felt was that the Formula One pit stop really approximates the kind of intense high-speed operation. So if we can get something to work for an F1 pit stop, then we can now apply it with a bit more confidence to a real-time emergency system. So what we looked at was the test case, which is this tire change operation in a Formula One pit stop, which is very slick, as you know, and a lot of people are well aware, and they've seen it on the television as to how it works. Let me go through it. So you've got up to 24 people working in a very close space, working together, in 2 seconds, changing all 4 tires on a Formula One pit racing car. And these teams are quite well structured, very well choreographed. It's a very slick operation. First of all, you need to get the tires there and you need to carry the old tires out. So you need 8 tire carriers, 4 for wheel on, 4 for wheel off, and 1 to remove the old tire, 1 to put the new tire back in place. You need 4 wheel gunners. These people take the locking nut off the tire and replace it and tighten it to finish the reinstallation. So again, tire off, wheel nut off, tire on, wheel nut on, and away they go. These teams are independent teams, but they work very closely together. And it's the same in all these teamworks. The slowest of them determines the overall speed that they can perform this operation. So all these interactions are valid and all affect the time. Then you've got the front and rear jackman, because before you can remove the tire, obviously you need to jack the car up, and they do this very quickly with a front and a back jack. Because you've raised the jack now, this racing car is unstable, so they need to stabilize it to stop it rocking. And because sometimes you get damage to the car, then the people standing by to replace nose cones or to treat the back spoiler, etc. So all these people working together in 2 seconds. And as well as that, you have the supervision. You have a lookout, basically looking to see where the gaps in the traffic are, so he can safely import and export its racing car. And you have another lookout, which is looking at the whole operation. The jack operation is very, very simple. It's just basically a lever arch. The problem is that the front jackman has to push the jack under the front of the car as it's arriving at him at about 60 miles an hour. So that's quite a dangerous situation. So in safety terms, this is the most exposed of the issues. The backman, though, once it's up, the guy at the back really he can now operate quite safely because the car is moving away from him. So the jack is quite simple, efficient, but is absolutely crucial, because if you don't raise the car, you can't change the wheels. So in terms of resilience, quite a few of these teams have extra jackmen standing by in case the jack doesn't work, and then they can whip it away and put a new one in. So the choreography of the tire change is very important. How you coordinate the wheel gunner, the tires, the jacks, etc. Very important in the slickness and the timing of the procedure. Also, as we were saying before, the front jackman has to get out of the way before they can lower the car and let it set off. And to avoid him getting trampled, there's a series of signals from the jacks and from the wheel gunners, which says, I've completed my task. And this is displayed at a traffic light, which is above the driver's cockpit, so he can see what's going on. The traffic light is telling him everything is ready to go. But in fact, they don't go until the pit stop boss actually does a final check to make sure everything is right. And if it's not ready, then he can override the ready signals. So in fact, it's not ready. And again, it's only until the lookout man tells him he's clear that they can let it go. But if there's a problem, then there's a real pressure in the system. And we can see in the pictures just how hectic it is in these systems. So we can build what we think is happening in the system. And this is the FRAM, the work as imagined, which we built from looking at the videos and looking at the information we have. And you can see we have to call in the car, stop the car in the box. Has to stop precisely in the box. You lift the end of the car. You can then take the front lug off the tire, remove the front tire, put the next one on, and then tighten it up. Once it's tightened up, you can lower the car. If everything's okay and there's a gap clear, then you can press the button and change the traffic light, and away you go. Quite busy, but quite as I'm sure you can see a very simple process. Actually, it looks, but it's not. The values that we need then is things like those functions that have to be activated before another activity can be initiated. And that's shown by the colored stripes that we can program into the value metadata. We're interested in how much that particular execution time, how long does it take to change a wheel, how long does it take to lower a car, etc. We have another value, key in a value, which we're calling the variability in the processing time. So we're not using this at the moment because this is just a demonstration. And then we're looking at the cumulative time that the whole process, in terms of how many instantiations have gone through at that point. And then the other thing which we are interested in for diagnostics is the delay in that function. Is that function held up, and what function is holding it up? So this is a value which we're putting in, which is true or false, which is there a delay or not? And again, we can use this display feature to show us on the diagram whether we have a problem. And we can calculate these time to process, execution time. We can estimate and put in a value. In this case, it's in seconds. The time to process is 0.1, for example, seconds. And the cumulative time then is the times, the maximum time is taken all through up to that process, plus the process time that we're doing at the moment. So these things then can be calculated and kept, stored, etc. So we can put in values that we think are reasonable. These are solely guesses. I mean, the object was to try out the metadata system, not to get a really accurate result. So the time to react, we've said 0.15 seconds. Time to complete stopping the car, well, it's the initial stop. Time to lift the car, 0.2 a second. These are notional, but I think they're sensible. So then you add these two together, and that's the time taken for that particular process. So we put these in and run the FRAM, the expected behavior, and we looked at it, and that gave us an expected time for a pit stop at 2.7 seconds. When we looked at the critical functions, it all made sense. Yes, you have to stop the car, you've got to lift it, etc. All makes sense. But when we looked at the video where they actually did one of these pit stops, the work as done rather than work as imagined, then of course we got a much shorter time. And again, if you look at the record time, which is something like 1.8 seconds, this is considerably better than our work as imagined would indicate. So what we did then is go back and look at actually what they did. And what they do is that they don't actually wait to start until that car is in the box. What they actually do, and you can see it here in this clip, the wheel gunners are removing the nut or engaging with the nut before the car has reached its stop marks, which are here. This is the stop mark where the middle of the tire is supposed to be here. So you can see they're anticipating, and also they're on there before the wheels, before the cars stop, and before in fact the jacks are in. The jacks are still on the sidelines. So the choreography and the assumptions that we made when we built the workers imagined were wrong. And the actual choreography the work has done meant that they're cutting corners. They're actually cutting, making adaptations to improve the process. So what we can do is show what actually happens. So as soon as it approaches, they start. And in fact, the wheel nuts are off before the front of the car is moved. Then they remove the tire, put the new tire on, then they lock the thing, and the car is lowered before, in fact, the tire, yeah, they're lowered before the tire nuts are tightened. So the whole thing is slicker. The whole thing is different to what the workers imagined would seem. So if I go to the next slide. Sorry. If we now put that into our workers done and we run it, then we come up, the workers imagined is 2.5 and the workers done is 2.15. So it's sorry, 2.7, quite a difference. So again, what's interesting is that in actual fact, in 2018, a Ferrari mechanic suffered a broken leg when Kimi Räikkönen was released too early. And the reason was then that they were doing this shortcut, this anticipation, and they dropped the car before they let the car go before the guy had got the jack out of the way, which broke his leg. So it all makes sense, and the numbers make sense. The handling makes sense, the values make sense. So basically what we're doing is concluding that it's demonstrated that the feasibility and benefits of using these values in the way we're using to extend FRAM's instantiations to quantitative instantiations for things like time looks like it's useful. And we believe it justifies its use now in our studies on the undertaking in Cardiff. And it is important because the time to process patients is crucial, both in experience. It's literally a matter of life and death in some cases. So we're hoping it's going to provide us, now we're going to build on the current work and see whether we can get more quantitative improvements, because management always like to see quantitative demonstrations of effectiveness, and we hope this will allow us to do that. Okay, thank you.